Hey, what's up, everybody? How's it going? In this video, I'm going to go through this Leetcode number problem 113, number 113, path sum, the second version of it. If you haven't done the first version, I recommend you to do the first version first, and that's a bit easier. And also, that problem actually built up an intuition for this problem. And let's dive in. And this problem was asked by Facebook and Amazon. So let's go through an example in here. So look at this binary tree in here. What we need to do is to return all the root to leaf path where the sum of the value in the path equals the target sum. Each path should be returned as a list of the node value, not only the value, not the node references. A root to leaf path is a path string starting from the root, ending at any leaf node. So in this example, we are given a tree looks like this, and the target sum is 22. And so there are two paths possible. One is 5, 4, 11, 2. So if we add the numbers along the path, so 5 plus 4 plus 11 plus 2, that's 22. So that's one path, and so that's one of the result. And the second path will be 5, 8, 4, and 5. And then if we add all the numbers, and then we get the same number, 22, which is exactly the target sum. And the example number 2 here is a 1. The left child is 2. The right child is 3. In this case, the target sum is 5. And there's no such path that can give up the target sum of 5. So it's return an empty list. So for this problem, the ideal approach would be use the DFS, the depth first search, instead of the BFS. I'm gonna talk a little bit about the BFS, why that is not the best approach in here. So I'm used a iterative approach to solve this problem, and after this, I'm gonna go through a little bit about the recursion approach, which is on the official solution, and mine is not following an official solution. That's why I want to go through in the video. So we first have a corner case where if the root node is none, and then we just return an empty list. And because this is a DFS, we need a stack. And there are 3 elements that we need to keep track of. One is the node itself. The other one is the remaining sum that can get us to the target sum. In the initial case, we have the number at the root, at the very top of the tree, and the target minus the root value is something remaining to get us to the target sum. And also we have the list that we can keep track of, because at the end we have to return a list of the numbers. That's why also I have a list that attached to each of the nodes, which we can append when we traverse along the path. So for the DFS, we use a stack, and first we pop it off from the stack, right? And because this we put the following in the while loop, and we first have a termination condition where if we are at the child node, a leaf node, that means for a leaf node, that means there are no child. That means the left node is none, and also the right node is none. And also the remaining is 0. That means we are exactly at the path where I can get us to the target sum. For that case, we append the list to the result. And if we are not at the leaf node, and we do the following, and as you can see, we have a very similar operations for the left and the right. So I need to go through I'm gonna go through just one of the this code, and then you understand the other one. So we look at the left side first, the left child. I call it temporary left node, and then also the remaining will be what is been passed through minus the value at the left child, and then we have the new temporary list that we will append the left child's value, and then we push it to the stack, and then the stack will bring it back to the top of the stack, and then we will go through the same thing again for the child of this left child. Same thing for the right hand side. I'm not going to go through the right hand side because it's exactly the same. So let's run that. Yeah, looks pretty good. Especially, I'm really happy about the memory usage because it's something that I was concerned about, because we have a this temporary list to keep track of to be that's attached to each of the node. I worry a bit about the space for this approach, but it looks okay to me compared to other solutions. So this is the iterative approach. Let's look at a little bit about the recursion approach, which is kind of similar. For the recursion approach, same as other recursion method, we first have a termination condition where if the node is none, and then we return, we don't do nothing. And then we append the value to the path node. So in the official solution in here, the path nodes, that's equivalent to the temporary list that I have on my solution. And if we are at the leaf node, and also the target sum, the path that we are at provides a target sum, and then we append to the result. Otherwise means that we are not at the leaf node, and then we keep pushing the left child, also the right child, back to the recursive tree, and then keep looping. And in this statement here, we just initialize the run and then keep at the beginning. So for a time complexity, this is a big over n square, which might seem counterintuitive, because initially I thought the time complexity is going to be only big over n, but it has a point where it says for every leaf, we need to perform a potential big over n operation of copying over the path nodes to a new list to be added to the final path list. So basically what it's saying is when we append that value that takes big over n, actually on my solution over here, it's saying that I have a copy of the temporary list and append the new value to it, and that takes a big over n, and we have to do that n times. So that's why it's big over n squared. So so that's time complexity. For space complexity, and it entirely comes from the temporary list that attached for each of the nodes. So that's big over n in total. And also it has a little bit discussion about why the BFS is not the ideal approach, and the reason is the memory usage. And so it discussed a little bit about BFS could solve this problem. And however, because the problem statement actually asks us to run a list, return a list of all the paths and add it up to a particular sum, BFS moves one level at a time, and that means we would have to maintain the path node list for all the paths until a particular level of depth at the same time. So let's say we are at level 10 in the tree, and that level have 20 nodes, and BFS uses a queue for processing the nodes. Along the 20 nodes in the queue, we would also need to maintain 20 different path nodes list, because there's no backtracking here. That's too much of space overhead. So this is exactly what I was concerned about the space, the memory usage. And so the BFS is not good for the memory use because you have to maintain um, a lot of memory for the term list. So that's why the DFS is better for this problem. So that's my solution for this problem. I hope this is helpful. If it is, please like and subscribe. That will be a huge support. Thank you so much for watching, and I will see you in the next video.